Alright, welcome back. Math 1910. We're getting into Chapter 3. We're taking a look at Section 2, and we're going to understand Rolle's Theorem and the mean value theorem as we go through this. Okay? So, the extreme value theorem states that a continuous function on a closed interval a to b must have both a minimum and a maximum on the interval, right? Remember, it's a closed interval in this case. So, those mins or maxes can occur on the endpoints of the function, okay, as we work through this. So, let's define Theorem 3.3, which is Rolle's theorem. Alright, it says, let f be continuous on the closed interval from a to b and differentiable on the open interval a to b. So, very important points there. So, we have to analyze if f of a equals f of b, then there's at least one number c in the closed or the open interval a to b such that f prime of c is 0. Okay, so kind of a lot to read through. We'll approach all these through a few examples. Alright, so let's take a look at this function here. Alright, we can see it's continuous on the closed interval a to b, right? There's no holes showing in the graph and all of that. Then we know that, it is differentiable if it's continuous there, okay? So we can see that we're not going to have any sharp points or anything like that. We know that we can take the derivative at c. Alright, we'll have a horizontal tangent line with a slope of 0. Oh, sorry, hit the button head there. Alright, and we have to find f of a and f of b. So if we look, f of a equals d, f of b equals d, so we can conclude that f of a equals f of b. So we have to know for a fact now that there's at least an x value somewhere between a and b where the graph has a horizontal tangent line, right? That means that's where the derivative is equal to 0. So we can, use Rolle's theorem and just looking and analyzing this graph, come up with those conclusions. Now, if we take a look and we try and do Rolle's theorem without differentiability, all right, we're still going to have that critical number at c, all right, but we may not get a horizontal tangent line at c, right? Because we're at that abrupt point. Just like when we had to deal with the absolute value function and things like that. All right, so let's roll through Rolle's theorem here. No pun intended. All right, but we want to find the two x-intercepts of the function f of x equals x squared minus 3x plus 2, and we want to show that f prime of x is 0 at some point between the two x-intercepts. Okay, so we have to find the x-intercepts. So that's just our algebra. We're going to take the original function and set the original function equal to 0 and solve for x. Alright, so when we do that, we're going to take x squared minus 3x plus 2, set it equal to 0. We can factor that down into x minus 1 times x plus, or x minus 2, and we set those each equal to 0. So we can say that x minus 1 equals 0 and x minus 2 equals 0. So that gives a solution, alright, that it can happen if we have x is equal to 1 or x can be equal to 2. Okay, so that's where our we set the original function equal to 0 and we solved for x. Okay, so what are we doing? Those are the endpoints of our interval now. Okay, so we're looking for where we have the derivative of the function is equal to 0, so we're going to have a horizontal tangent line between the two x-intercepts. So these are now the interval that we are going to analyze between x equals 1 and x equals 2. So that's why we found those. Okay, so we substitute those in because we have to verify that we can use Rolle's theorem. So if we use f of 1, we get 0, and f of 2, we get 0, right? We substitute 1 back into the original function, and we substitute 2 back in the original function, and we get back 0. So f of a does indeed equal f of b. So we know that we can apply Rolle's theorem, and we know that there exists now at least one c on that interval from 1 to 2, such that f prime of c is equal to 0. Alright, so let's take the derivative of the function. Alright, so we can find out that f prime of x is equal to 2x minus 3. So we took the derivative of the function, and now we're going to take that function and set it equal to 0, the derivative. Alright, so we set the derivative equal to 0, so 0 equals 2x minus 3. Alright, and then we solve for x. So we add 3 to both sides and divide by 2. So we can figure that out so that when f prime of x is 0, alright, when the derivative is 0, that occurs when x equals 3 halves. Alright, so if we take a look at the function here and graph it, And we looked at the endpoints, so we're looking between x equals 1 and x equals 2. And we're looking at the critical value here when f prime of x equals 0. Okay, so we did that and we calculated that to be 3/2. Okay, so that's where we have a minimum in this case. We have a horizontal tangent line, all right, and this occurs at the minimum of the function. All right, next thing we're going to take a look at is the mean value theorem. Okay, so we can use Rolle's theorem to prove the mean value theorem. And remember, the word mean means, average. Okay, so think about that. So let's take a look. We got theorem 3.4. It's the mean value theorem. It says if f is a continuous on the closed interval from a to b and differentiable on the open interval a to b, then there exists a number c in the open interval a to b such that f prime of c is equal to f of b minus f of a divided by b minus a. Well, lo and behold, you should recognize that as slope, right? y2 minus y1 divided by x2 minus x1. So essentially the slope that you've learned about all these years, it's really just the mean value theorem in essence, okay? So let's do this function here. We have f of x equals 5 minus 4 over x. We want to find all the values of c in the open interval 1 to 4. All right, so we're going to find f of 4 minus f of 1 divided by 4 minus 1. All right, so that yields 4 minus 1 divided by 4 minus 1, and we get 1. That's defined as the slope of the secant line. All right, why is it the secant line? Because it's through 2 points. Remember, the secant line requires 2 points to calculate it. All right, so as we work through that, that's really all we're doing with using the mean value theorem. Okay, so it satisfies all the different conditions that we're looking for. So that one relatively easy, right? We just plug in y. It's really just y2 minus y1 divided by x2 minus x1. So you've been doing that since whatever, 6th grade, 5th grade on that one. All right. So, but if we move forward, right? So if f is continuous on the closed interval 1 to 4, and it's differentiable on the open interval 1 to 4, all right, we can conclude there exists at least one number c on that interval 1 to 4 such that f prime of c is equal to 1. So what we need to do, right, is we're going to take the derivative of the function and set it equal to 1. All right, so we're going to take f prime of x and set it equal to 1. So we have 4 over x squared is equal to 1. All right, and then we solve that for x. We square root both sides and we get plus or minus 2. So that helps us conclude, right? We've discovered on that interval, so we did f of a minus f of b all over b minus a, right? And that yielded what we were looking for so far, right? That would be the slope of the secant line. That is what gave us 1, right? So then we had to set the derivative equal to 1 to find out where that happened. And that happened at c was 2. So think back through the steps that we did for this problem. Okay, we analyzed the interval. The interval was from 1 to 4. That was our values that we had to plug in and find. So we did f of b minus f of a. So we had to substitute in, 1, all right, and we had to substitute in 4. So that ended up giving us f of b minus f of a all over b minus a, right? We substituted all that in, and we got 1. Then we can conclude, right, we found that value of c. We set the derivative equal to 1 and solve when the derivative was 1. Okay, remember the slope of the secant line in this case was 1. So that's how we solve that when we want to find this using the mean value theorem. And that's how we find that value of c, all right, where that value actually occurs, all right? So we had to verify that we met the conditions for the mean value theorem, then we had to apply the mean value theorem, all right? Now, there's an alternate form to the mean value theorem. You might recognize this one maybe more as like a point slope type scenario if we take a look at this, okay? So this is where that comes into play. So if f is continuous on a to b, all right, the closed interval, and differentiable in the open interval a to b, then there exists a number c in ab such that f of b is equal to f of a plus b minus a times f prime of c. All right, so just note, remember, polynomial functions, trig functions, all differentiable on their open intervals. Okay, so we want to determine whether or not Rolle's theorem can be applied to the function f on this closed interval a to b. All right, then if Rolle's theorem can be applied, we want to find all the values of c in the open interval that exist where the derivative is equal to 0. The set, so we're going to find f prime of x as 0. Okay, so we have the function f of x equals negative x squared plus 3x, and we are on the closed interval from 0 to 3. All right, so the first thing we need to do is find f of a and f of b. So f of a is 0, so we have to substitute in 0 into the function. So we're going to get negative 0 squared plus 3 times 0, which yields 0. We have to find the f of b piece, right? So we're going to substitute in 3, all right, for x. So we're going to get negative 3 squared plus 3 times 3. That also equals 0. Note that negative is in front of the x. It's not in parentheses, so it's not getting squared. So we've met, the conditions for Rolle's theorem. Remember, f of a had to equal f of b, so we do meet those restrictions that are on it. Okay, so those conditions allow us to do that. Then we can apply Rolle's theorem. So we're going to find f prime of x. So we take the derivative of the original function. Okay, the original function is negative x squared plus 3x. We take the derivative of that, we get negative 2x plus 3. We set the derivative equal to 0. So 0 equals negative 2x plus 3. And when we solve for x, we end up getting 3 halves. So for us, first step, we had to check, can we apply Rolle's theorem? We proved that, right? F of a had to equal f of b. And then we were able to find all the values of c in the open interval where the derivative was equal to 0. So our c ended up being 3 halves. Okay? All right. Moving forward, next example here, we want to determine whether Rolle's theorem can be applied to f on the closed interval from a to b. And if Rolle's theorem can be applied, find all the values of c in the open interval a to b such that f prime of x is equal to 0. All right, so we're given this function here, f of x equals the quantity of x minus 4 times the quantity of x plus 2 squared. We are on the closed interval, negative 2, 4. So first thing we have to do is check whether or not we can apply Rolle's theorem. So a is negative 2, b is 4. So we have to evaluate negative 2 and negative 4. So f of a, when we substitute that in, we get 0. F of b, when we substitute 4 in, we get 0. So f of a does in fact equal f of b, so we can now apply Rolle's theorem. So we need to take the derivative of that function. So we've got a product rule and we've got a chain rule as we're going through. Okay, so when we work through all this, the derivative, all right, f prime of x ends up yielding 2 times x minus 4 times the quantity of x plus 2 plus x plus 2 quantity squared. Okay, so when we work through all that and we solve, we can see that one solution is when x equals negative 2. All right, that's when the derivative will be equal to 0. So we would set f prime of x equal to 0, solve for x. We can clearly see that negative 2 is one solution there. Now, the other solution, right, is 4, but it's an endpoint, so we necessarily don't want to conclude it because we want to find between a and b, not at a and b. And we're talking about the open interval from a to b, so that means we cannot use 4. We can only use negative 2 in this case. And can we? Because we're on the interval. So we got to think about this. Okay, I just said we can't use 4 because we're on the interval, and we can't use negative 2 on the interval, and 2 right. But what we can conclude, all right, is where that lies. So we got to think about some things. So we're looking when x equals negative 2 and when x equals 4. So the issues for us end up being on the interval. So we got to check, all right? Can we apply this? No, because we're talking about the endpoints there. So x equals -2. Okay, so we can't really find anything inside the interval. We can apply Rolle's theorem, but we can't find a value of c that sits inside there. Okay. All right, example 6. We're going to determine whether the mean value theorem can be applied. All right, and then if the mean value theorem can be applied, find all the values of c in the open interval. So we have the mean value theorem, right, states that f prime of c is f of b minus f of a all over b minus a. So we are given the function f of x equals x squared on the closed interval -2, 1. So we have to find f of b, we have to find f of a, and then we're going to apply f of b minus f of a all over b minus a. So a is equal to -2, b is equal to 1 in this scenario. So when we substitute everything in, we're going to get 1 squared minus the quantity -2 squared divided by 1 minus the -2, which yields a -1. So now we're able to take the derivative, all right, f prime of x. All right, so f of x was x squared, so f prime of x is 2x. All right, now we're going to set 2x equal to -1. So x is going to be -1/2. All right, so this is what we're doing. We're using the mean value theorem, all right, to apply here. We see if it works. So we get f prime of c is equal to -1. We take the derivative of the function. All right, then we plug in f prime of c, which is -1, into the derivative of our function and solve for x. And that tells us what our c value is on that open interval, all right, where the slope is equal to -1. We're trying to find where the slope is equal to -1. So that's how we approach this problem. So that's the end of this lecture. If you have any questions, please feel free to email me or let me know if we need a Zoom call or team call or anything along those lines and go over anything else. Guys, have a great day. I'll see you in class.